Welcome back, ladies and gentlemen. And now we shall quickly proceed to our second keynote talk of the day, which has the task of elaborating more to us on why is there a need for explainable artificial intelligence. This talk will be given by Dr. Dorothea Wisemann, who is a leading technologist and department head of the Cognitive Computing and Industry Solutions Group at IBM Resarch, Zurich. In this role, she directs a team of researchers with a broad portfolio of activities including AI, blockchain, healthcare, computational sciences, robotics, security, data privacy, and much more. So, without any further ado, I would like to introduce Dorothea Wisemann. Thank you.
Thanks. Thank you. So when I actually started preparing the presentation, I was thinking, maybe just talking about the need for explainable AI is a little bit on the thin side. So what I will be doing is I'll basically touch 3 blocks. First, I'll pause a little bit and step back and say, well, what's the need? Let's see. For AI, right? Why do we have this explosion of machine learning, cognitive AI, however you want to call it, data science, right? There are these many names. We prefer AI. And just stop for a moment and say, why now, and why do we see so much of it? And also define a little bit, what do we mean by AI, and give just 2 examples out of my own department, what do we do? And then I move to, well, why do we need explainable AI, right? So why can't we just work with the models we have, right? We just accept them and we just take their predictions and go and run with it. And then last but not least, the need itself is, of course, not satisfying, right? I'll also show a couple of methods on actually doing explainable AI and explaining and interpreting AI models. So that's going to be roughly the 3 blocks. So let me start with the need or the opportunity for AI, if you will. And so if you look at these 3 curves, right, those are, if you look back at IT, data science, like our industry, it's really been governed by these non-linear growth, not quite exponential. I go through that, right? For those older in the audience, remember the Moore's law, right? This was about the number of transistors on a certain area doubling every year, every 18 months, and thus the compute power doubling every 18 months, every year. And some of the models, honestly, that we train today, the deep learning models, they wouldn't be possible if we hadn't had that explosion in compute. Then the next law that has governed our industry is Metcalfe's law. And what that is about the power of a network. And so that says that the power of a network actually grows with the square of the number of users, right? The more users you have, and with the power law, the power of that network grows. So that's the second one. And you could argue, initially, Metcalfe was, it's actually named after him because his involvement in the Ethernet. So this was really about physical networks. But if you think about it, it's also about communities, right? Social networks. The power of these networks has been growing as we have been increasing the nodes or users involved in that. And then comes this last curve, or the most recent curve, that is actually governing us, I think, in this room today. And that's the explosion of data. And so we call that Watson's law, right, after our founder. You may call that differently. But the fact is that data has been, the amount of data, structured and unstructured, that's out there, that's being produced every day, has been growing exponentially. And so if we want to use that data and turn it into knowledge, we need artificial intelligence, modeling, cognitive, however you want to call that, right? And the more we bring to that, the more we make out of the data, the better our models get. So that's actually a self-feeding, positive feedback loop. So therefore, we think that the knowledge growth can actually be even faster than the data growth. Now, what do we mean by, so therefore, for us, it's one of the, what we call strategic imperatives, developing core AI for us and our clients to make sense of that data and harvest the power that's in that data. What do we mean by AI? Maybe I need to point in the other direction. So we distinguish between 3 groups, types, parts of the spectrum. So first one is narrow AI, and we see that a lot of industry has starting to use what we call narrow AI. Narrow AI it uses, in our description, relatively narrow set of data in the sense of data type to perform a relatively narrow defined task, right? So that could be images to identify cats, or maybe perhaps a little bit more useful, images to identify manufacturing defects. But we have one type of data, and the AI is capable to perform that task. It's not very flexible, right? If it can't do neighboring tasks, it's just trained for that and is able to do that. And then at the completely other end of the scale, it's the computer can do everything, right? There's a little bit the science fiction portion where we have the computer that can perform any task based on its learning. And then the middle is the broad AI, and that's where we are roughly now. We are at the beginning of the broad AI, where we say we can take different types, multimodal data in for systems to perform richer tasks, for systems to reason about their outcomes, for systems to debate. If you've seen the IBM debater lately, who's been debating with a human whether we should invest into space exploration. So this is this middle portion where we stand at the beginning, where we go beyond having data models trained to perform very narrow tasks. And those are just 3 examples of what we mean by that, right? The first one I alluded to is taking a richer multimodal data set to perform the task. In medical, for instance, it would be about bringing together electronic health records. So that's mostly textual data with images from the various investigations, right? Radiology, for instance, with time series data about blood pressure, for instance, and combining all of those to diagnose. Or in this case, it would be what we've seen quite a bit is like this combination with pictures and figure captions, right? Quite amazing what the systems can do, start to do with generating figure captions for quite complex pictures. And then the second one is about going from just scalable machine learning to reasoning, debating, etc., to make a case rather than just making a prediction. And then last but not least, as another type of broad AI is interaction, right? It's really another new dimension coming from, let's say, prediction models to interacting with humans. And we see it's really, if we look across our clients, if we look in the industry in general, and I think this is reflected in the full audience today, that every business is actually embracing data science or AI, right? Be it financial services, where it's used for credit risk scoring or fraud detection in real time, or in supply chains, where you may be demand forecasting, etc. And we see this everywhere. And I just wanted to pause here for a moment and just say, where do we apply? Just bring an example from the research lab. Where do we actually introduce AI? And one of the projects that I think is the most interesting to me personally is how do we actually change research and development with AI, being in a research lab. And so if we look at how does R&D or in development in general, and I'm going to use an example of materials development, where we're actually working with a company out of the region also to develop metal alloys using AI. And so if we look in general how development is done today, it's really on 3 pillars. On the one hand, you have your theory, your knowledge, it's often in the brains of people, like people who have been trained to be a chemist, for instance, who are reading scientific papers and keep themselves up to date. And then if they think about a new material, for instance, they may have a hypothesis based on their knowledge and then go either into simulation or experiment, right? It's typically a ping pong between simulation and experiments. And so how do we think AI can help in that 3-pillar research and developing methodology? So the first one on the knowledge, we think we can help tremendously if we bring the knowledge that's out there, the scientific knowledge that's out there, to the fingertips of the researcher or developer. Now, okay, we do have Google, right? I mean, we can Google about a lot of information and knowledge bits, but a lot of the scientific knowledge, and that's not so different from a lot of knowledge in the businesses, is stuck in documents. And so what we've been looking at is really reading documents, for instance, all patents, all Nature publications, all physical ref letter publications of the past, ingesting that, extracting that knowledge, and making it available to the researchers. So that's the first one, and it's actually complementing, let's say, the search engine for the knowledge that's out there in the web. Second is, once we have that data basically extracted from, I don't know, 30 years of patents, then we bring this into a representation. It's would be typically a graph representation of that data, and then we can draw inferences. So now we could use that data not just to search on it, which is also portion, but to then run our models to come up with new predictions, new hypotheses about things that could work. And then last but not least is the evidence and experiments, and that's really to help the researchers to bring that data in a searchable manner to their fingertips. So let me give concrete examples of what we've done here. So the first one is these parsing of the documents. And so these are largely PDF documents. If we think about patents or publications, and the essence is, of course, everybody can read PDF, right? But the portion about the interesting bit on information extraction, and we had that yesterday with the presentation about the keyword extraction, we think the interesting bit about information extraction is to emulate a human as much as we can. So I don't know how often you read patents or maybe publications. What do you look at? Do you read from A to Z? I don't. I read title, figure captions, and affiliation of the author. That's the first three things I look at, right? Patents, I look at claims, right? So I go fairly straight to, I would almost say those are the concentration of information. And so we thought, okay, if we want to extract knowledge and have really concentration points extracted, and not all the intro sentences in addition, then we need to understand the structure of our documents so we can zoom to those concentration points and then extract selectively from there with a much higher quality. And so anybody who's done PDF extraction knows that that's not trivial, right? There's some tools out there with a lot of limitations. So we invested into a super scalable, structure-aware PDF extraction methods, so we can read, and this is the example, it takes about 30 seconds on a laptop to read 20,000 papers. So that's the first thing. So now we have the knowledge. Another example, so what can we do with this now? So here, this is about chemistry. It's about predicting, ultimately it's about predicting the reactions of organic chemistry. And I personally was not the best organic chemist. That's why I went into physics and computer science. But it's hard, right? It's hard for many people, including chemistry college student. And so what we thought, okay, can we build a model to actually predict the outcome? So what we've been doing, in this case, we didn't extract ourselves, but it's basically done by Lowe, extracting from the US patents all the organic chemistry reactions that have been patented, right? So input material, the input molecules with the reactants if needed, and the output. So that creates a corpus with about 1 million reactions. And then we trained a neural network on that, and we thought, could we use seq-to-seq, right? Houston translation isn't a chemical reaction a translation, ultimately, right? So you could argue the molecules are words, and ultimately we translate from the prior to reaction space to the reaction. And so that's what we tried. We used a seq-to-seq deep learning model to predict the outcome of the chemical reactions. We are in the 87% correct. We had it presented at the ACS, that's the American Chemical Society meeting a month ago, and everybody can try it. It's out there for free. Go out and try it. We actually have a challenge, humans against machine. And at the ACS, where you expect, those were the subject matter experts, right? American Chemical Society meeting. For those who, I think when I looked after the first day, it was 10 to 6, humans against machine. So we've been faring quite well, and we think this is a nice way to bring AI into school, into college, into the leisure chemist, to support them in predicting some of the outcomes. So we see AI adoption, right, across the board, just to come back to the main theme. And just a couple of numbers, right? 94% of the companies believe that AI is key as a competitive advantage. And then there are like in AI associated to customer relation management, the companies believe that the revenue is boosted by 1.1 tera, I guess that's billion dollar in the next, between 2017 and 2021. But, there's a but. We also see that if we then look who's really brought the AI into their business processes, right? Versus having some models that's maybe run in the back office, not in the critical paths, etc. We see that only 1 in 20 companies really extensively incorporated AI in their businesses. And there are multiple reasons. Some are shortage of data scientists, so that's good news for the room. But there are also other reasons. And I think the last one is one that we actually see, also me personally, when I work with clients, is an essential one. That as we see in this survey, actually only 35% of the decision makers trust their models or trust the models that are in their company. And while we may follow recommendations on Amazon, so I also pick Amazon as an example, on what other clients have also bought. And I don't know whether you're thinking it's not fish tank accessories, it's actually cat toys in this case. So indeed, recommender systems if you think Amazon, eBay, Netflix, they work beautifully, right? I think the numbers are 35% of the Amazon purchases come from recommendations, 47% of the eBay purchases, and a staggering 75% of the Netflix downloads are based on recommendations. So there are areas where we just trust it. And honestly, it probably doesn't matter if the other users haven't bought the little toy on the right. Right? It probably doesn't matter. And in the worst case in Netflix, I spent 2 hours bored. But would we trust a system in the medical domain? Says like other patients with the same characteristics and symptoms have been successfully cured by this disease, just without any explanations. Do we like to trust it in the financial services if we are denied a credit? So the problem is there are areas where it's fine to just trust it because what's at stake is not that big, right? $10 for a cat toy. And then there are areas where it really matters whether what the model recommends, the prediction that the model does, is correct. And for those areas, it is legitimate to request that you can explain the model. And besides the point, with GDPR, we all data owners have a right to ask, right? So if your bank denies you credit, you have the right to ask if an AI model was used, but why? So it is, in order for AI to really penetrate in these essential decision-making areas, we need to be able to explain our models. But there's hope, right? There's a lot of research going on. If it goes back, the first ones that I'm going to show go back to 2009, but we've seen a real explosion in scientific work on explainable AI in the last 3 years, I would say. I've just looked at the NIPS program is out. So that's the biggest AI conference, if you will, sold out already. It's going to be in December. So the scientific conference is sold out now for that conference. That's in December. So this is the conference. And you can see if you browse through the program, there is a lot of work going on. So what I want to do in the last part of the presentation is show a couple of examples how you can explain AI. And I'll pick some of the well-known works, right, just to compare and contrast, and I include 2 of the very recent works from my colleagues in the US who are already in ArchiveX and will be presented at NIPS just to show what's out there. I'll keep that relatively high level. I mostly want to present the intuition about how these models are explained. I have references for all the papers at the bottom, so you can read about the math in detail if you want to afterwards. And so first I want to say is, because we use these explainable, interpretable models, right? So what's the difference? I want to start with the definition, really, what I mean if I say explainable, and what I mean if I say interpretable models. And I follow Gregoire Montavon for that by saying, interpretability is so he has a fairly complex definition, but so he says is if I can map the outcome, the output of the model back into the input space. Let me formulate it slightly different. Interpretability is if I can, and now I'm doing a mix of the terms, explain the whole model. Right? I can explain the model for all its possible predictions in the future, right? I really explain what it has learned. So that's interpretability, the whole model. Explainability, in contrast, he defines as explaining an individual prediction, right? So if I'm denied credit, hopefully that won't happen, then the bank can explain why I'm denied. Probably I would be granted credit because I'm female, but right then those are the factors that would be shown, right? It's income, it's often, and by the way, that brings us into bias, but I'm not going to touch on bias, right? But that's why it's important. Another aspect why explainability is important, because it also would surface bias if you start to need to explain certain predictions. So explainability is giving the reasons, more scientifically speaking, the features that led to an individual prediction. So those are the 2. I'll start with the top one, because of course, if I can interpret a model, so I can explain all its predictions, that would be preferred, because then I'm done, right? Once and for all. That's why I'm going to start with that one. The first one is, so how can you do that? How can you actually interpret a whole complex model? So maybe I'll pause also for a second. What models do I mean? I will be speaking mostly about deep neural networks, because those are the powerful models that we use today. In general, it would apply, some of these methods apply to all black box models, some are specifically for neural network models. So those will be, by default, if I don't say what I want to explain, it's a neural network. So the one option to interpreting a neural network model is by generating prototypes for classes. So assume we solve a classification problem with our neural network, then what I could try to extract once the model is trained is what are the prototypical instances for a certain class. And so we see 2 examples. The earliest work actually comes out of Benjer's group from 2009 already, and they extracted the prototypes for the MNIST dataset, right? The handwritten character dataset. And you see, that looks quite reasonable, right? So if you would say, this is what the model has learned, so this is, by the way, a way to then just assess my model, right? Not even arguing a specific prediction, but sort of assessing, does it make sense what it has learned, right? A sanity check. And if you look at that, and those are the prototypes that the model has learned from the handwritten characters, looks quite reasonable. So this is 2009. There has been a lot of work in the meantime, and I wanted to include a very recent, or relatively recent, actually 2016-17 paper where this has gone, because I think it's really amazing. So this is for, I think this is the CIFAR 10 or CIFAR 100 image collection data set. And so what that group has been doing is they've extracted the prototypes for certain. So this is a large image classification data set, right? So that the images are classified as you see in barns, candles, beetles, and specifically a leaf beetle, a badger, right? And different animals, different images. And so if you see what they've extracted as prototypes for these image categories, I personally find it's amazing. And if you see that, you see it's not a true image, right? But you see a candle. I mean, it obviously got something cylindrical going up with a fire on top. And the badger, it has the stripes, right? And then some roundish little animal. So I think it's really powerful. How is it done? Just again, staying at the intuition level, what is done is basically the idea is you take a random input image and then you vary it to maximize the activation of the final node for that class, right? Your final layer has the nodes for all the class, and you try to maximize the activation of the neuron in the final layer for that class of interest, and you perturb your input image until that output is maximized. One catch, if you just do that, if you really just do that as an optimization, you get unrealistic images, right? You get random things in your image. So you need to do one constraint if you do that, and basically constraining these perturbations to your actual data manifold, right? So that you get that your perturbed images could still be real images. Otherwise, you get well, crap. I'm going to call it crap. But so you need to basically constrain. The early works put something like a notion of an expert in there. The late works use guns, right? Adversarial networks, because they are trained to come up with realistic yet artificial images. So you basically use GANs to restrict your perturbations to realistic images, and then you do the activation maximization. Quite impressive. Now, I want to also show some work that's done by the US colleagues. We still do see with some business users, they love the models they have, right? Let's be realistic. If you've been using decision trees to determine, or basically, or to predict whether, in this case, it comes from manufacturing, and the example that they use is the metal edge quality of silicon wafers, and they are used to